Good evening, GCC. We're going to finish Chapter 6 today. Looking at 6.9, building exponential and logarithmic models. It also includes the logistic model that we skipped in 6.8. If you want to look over it, it's a good model for population and for other things. But I want to focus mostly on exponential and logarithmic. And remember, we can have exponential growth and exponential decay, and logarithmic growth and logarithmic decay. So I want to focus in on one of these. Now, the homework only has 3 problems from 6.9, problems 1, 5, and 11. They're all very similar. So what I'm going to do is we're actually in class, we're going to do problem number 4. So number 4 on page 500. So if you want to take a moment, take out your textbook and open up to page 500 and look at problem number 4. All right, follow along as I read it to you. It says chemistry. It says a chemist has a 100-gram sample of some sort of radioactive material. He records the amount of radioactive material every week for 7 weeks, and he gets the following data. So let's copy down this data table. So we've got the week and the weight in grams of how much radioactive material. So week 0, the starting, he had 100 grams. 1 week later, he measures it, and now there's only 88.3 grams of radioactive material left. In week 2, there's only 75.9 grams. Week 3, 69.4 grams. Week 4, 59.1 grams. Week 5, 51.8 grams. And it seems like I've come to the end of my piece of the paper here. So let's continue this table. Week 6, 45.5 grams. Now, this is very interesting here, because if I said, well, I don't know what this radioactive material is, but if I asked you, what's the half-life of this particular radioactive material? In other words, how long until only half of it was left? Well, we started with 100 grams. How long before we only had 50 left? Somewhere between 5 and 6 weeks. In week 5, I had 51.8. Week 6, I had 45.5. So somewhere between 5 and 6 weeks is the half-life. That's actually going to be one of the things that we're going to calculate a little bit later. So this problem has got several sections to it. Let's take a look at all the things that we want to do. First, so there's the data table. Part A. In Part A, it says, using a graphing utility, draw a scatter diagram with the week as the independent variable. Graphing utility means a calculator. So here I go. Here's my calculator. And I want to, let's see, make sure there's everything's all nice and clear out of there. So I want to enter the data and create a scatter diagram. All right, so there's my data. So I'm going to go to Stat, Edit My Lists. Let me move this over. Let me get this oriented nicely so we can see everything that's going on here. There we go. Stat, Edit, hit Enter to edit my lists. And I've got list 1 and list 2. Oh, I got a whole bunch of junk in there from the previous list. I want to clear that out. Well, I could go over and delete it, or second plus, which is the memory manager. Go down to number 4, clear all lists, and it'll do it for me. So now go back to Stat, Edit, edit my lists, list 1 and list 2. And I want to enter all the data. List 1 is going to be the weeks. So I'm going to have week 0, 1, 2, 3, 4, 5, and 6. List 2 is going to be the corresponding weight. 100 grams, 88.3, 75.9, 69.4, 59.1, 51.8, and 45.5. So I'm going to double check this here. 0, 100, 1, 88.3, 2, 75.9, 3, 69.4, 4, 59.1, 5, 51.8, 6, 45.5. Now, if you don't have this in there, go ahead and hit pause until you've got all this data entered, and we'll move on. All right, so the next thing I want to do is we're going to create the scatter plot. So now, how do I do the scatter plot? Well, I have to let the calculator know I want to do a scatter plot graph. So I have to go to second y equals, see where it says stat plots up there? Second y equals stat plots, and I have to turn them on. So I'm going to hit enter, and I'm going to turn them on. So now that's telling the calculator I want a scatter plot. Now, what type of window do I want here? Well, the x is the weeks, 0 to 6. I'm going to go from 0 to 10 weeks, scaled in 1 week increments. 0 to 10 weeks, scaled in 1 week increments. The y represents the weight. It's 100, and it gets less and less and less. I'm going to go from 100 grams, or the minimum of 0 grams, to 100 grams, scaled in 10 gram increments. So on my graph, I'm gonna sketch it in my notes here. My graph is going to look something like this, where this is the number of weeks, and this is the amount in grams of the radioactive material. So now I'm going to go to Zoom, which is my preset window, Zoom Stat, number 9, hit enter, and I've got a box and whisker plot. I don't want box and whisker plot. Let's go back to second y equals. Yeah, see, I had it set to box and whiskers. That's not what I want. So I'm going to change the type now to just do that first type right there, which is just a plain old scatter plot using list 1 and list 2. I didn't catch that. I had my settings set differently. So my second y equals, turn the scatter plots on, regular scatter plot using list 1 and list 2 with little boxes, make it blue. All right, now let's graph it. There we go. Now I'm going to sketch this. So I've got, it looks like something here, and then week 1, week 2, week 3, week 4, week 5, and week 6. So there's my scatter plot. All right, so that's part A. There's my scatter plot. Part B, using a graphing utility, build an exponential model from the data. So now I'm going to create a model from this data. So here comes part B. Again, it's all on the calculator. So now I'm going to go to Stat, go over to Calculate, and part B tells me I want an exponential model. So I'm going to go down until I see exponential model. Let's see, linear, quadratic, cubic, quartic. There it is, exponential regression. Hit enter. Using list 1, list 2, hit enter. Calculate. And here's what it's telling me. It's telling me that it's giving it to me in the form y equals a times b to the x. And specifically, the calculator says that y equals 100.3 times 0.8768 to the power of x. Notice I've got my correlation coefficients on too. This data is very strong. This is very strong. I could graph this on top. If I type this into my calculator and then graphed it, I could graph the exponential decay on the top. But I don't think that the calculator wants me to do that. It wants me to change this form. So question C says, so this is an exponential form. Question C says, express the function found in part B in the form of amount as a function of time equals an initial amount times e to the kt. So I want to rewrite this. All right, so I've got this, but I want to rewrite it like that. Well, this is equal to that. Amount of the function of time is y. So if I set these things, so really this is my initial amount, 100 times 0.8768 to the x equals 100 times e to the k t. All right, well, the initial amounts are the same, so we'll get rid of those. And it looks like I've got too many variables here, but hang on. So now I've got 0.8768 to the x equals e to the kt. But x and time in weeks, they're the same thing. So those are going to cancel each other out. So now I've got 0.8768 equals e to the k. Now I've got an equation I can solve for my constant. I want to solve that for k. No, I'm just going to... The board, I've got a lot more space. I can really spread stuff out. All right, so solve this for k. Let's get k out of the exponent by taking the natural log of both sides. The natural log of 0.8768 equals the natural log of e to the k. And of course, the whole reason I'm taking natural log is because it undoes the e. So now I've got k equals whatever that is. On the calculator, natural log of 0.8768 is negative 0.1315. I'm going to say negative 1.1315. So putting this all together, I want to put it back into this format right here. So my new formula, the amount as a function of time is the initial amount times e to the k, negative 0.1315 t. So here it is. This is the answer to part C. Here is the function that I found in part B expressed in the form of a sub t equals a sub 0 times e to the kt. Now it says I want to graph, part D, graph the exponential found in parts B or C on the scatter diagram. So here's my diagram. So I'm going to go to y equals now. I'm going to put this one in. 100 times e to the negative 0.1315x. And I'm going to graph it on top. Hit graph. And there it is. Boy, that's really strong, isn't it? It doesn't hit every point exactly, but they never really do they? But this is very strong data. It's very close. That R value is a really high value. So that's part D, graphing it on top. We just did that. That's part D. If I went back to my original sketch, where is it? There it is. It would look something like this. Part E. From the results in part B, determine the half-life of the radioactive material. So what's the half-life of this radioactive material? All right, so I'm going to take my equation that I got in part B. What was that equation? Where did it go? There it is. So in part B, I have, so this is the answer to question, what question are we up to now? Question E. And E says, from the result in part B, there it is, y equals 100.3 times 0.8768 to the x. It says use that to find the half-life. All right, so how am I going to do that? Well, if I this represents my time here, the half-life. So if I start with 100.3, how long before I've got half of that, which would be what? 50.15 equals 100.3 times 0.8768 to the x. Divide, and I get 1/2 equals 0.8768 to the x. X is in the variable again. We're going to use that logarithmic trick. Take the natural log of both sides. The natural log of 1/2 equals natural log of 0.8768 to the x. The natural log of 1/2 is the same thing as 0.5. And move x here using properties of logarithms. The whole reason I'm taking the natural log is so that I can move this variable and get it down out of the exponent. X times the natural log of 0.8768. Now the natural log of 0.5 is just some number. We can do it on the calculator in a minute. The natural log of 0.8768, that's just some number. I'm going to divide both sides by that number. And I'm going to get the natural log of 0.5 divided by whatever that is. The natural log of 0.8768. That's going to be my half-life. All right, on the calculator now. The natural log of 0.5, close parentheses, divided by the natural log of 0.8768, close parentheses, equals, and I'm getting 5.27, I'm going to say 5.3. 5.3 what? What is that? That's the half-life, the amount of time it takes to get half of the material. But that's time. What was the unit of time that we're studying here? Weeks. So my final answer, the half-life, is going to be 5.3 weeks. And didn't we kind of say that initially? In our initial data table, when we looked at the first data table, gosh, where did that go? Here was the initial data table. Didn't we say somewhere between 5 and 6 weeks it was going to be half of what we started with? And sure enough, there it is, 5.3 weeks. All right, and then finally, part F, how much radioactive material will be left after 50 weeks? So part F, how much will be left after 50 weeks? All right, well, I have the formula that I can substitute in. My formula from part B, and I really could have used either formula, y equals 100.3 times 0.8768 to the x, where x is time. How much is going to be left after 50 weeks? The amount left after 50 weeks, 100.3 times 0.8768 to the 50 weeks. Calculator time. 100.3 times 0.8768 to the power of 50. And it looks like 0.14. All right, well, what does that mean? What are my units here? Well, how much? How are we measuring how much? By grams. So my final answer is going to be 1.14 grams. After 50 weeks, there's only going to be 0.14 grams left. All right, ladies and gentlemen, you'll see that the other ones are very similar to this. So what I'd like you to do now is I want you to do homework 6.9. It starts on page 500, and I want you to do problem numbers 1, 5, and 11. Very similar to the one we just did. The numbers are going to be different. It might be growth instead of decay, but that doesn't matter. Growth or decay really doesn't matter. It just matters if the k value is going to be positive or negative. And then as soon as you've done this, email me the completed assignment. All right, guys, we're done with Chapter 6. Next, we'll be skipping 7, 8, 9, 10, and 11, and we'll be jumping into 12. For the last chapter, we're going to do pretty much everything out of Chapter 12, and then a couple of things out of 13. So hopefully you're staying up with this stuff. Keep working. If you've got any questions or things give you a hard time, shoot me an email. Make sure you're not just copying answers out of the back of the book. You're not going to get any credit for that. And keep working, guys. Good luck, and I'll talk to you again soon. Bye.